In number 136, we're asked to find the y-intercept, which means we're going to replace x with 0. So g of 0 is equal to negative 2 times 3 to the 0 minus 1 power. That's negative 2 times 3 to the negative 1, which is negative 2 times 1/3, or negative 2/3. In ordered pair form, we have the point 0, negative 2/3 as the y-intercept. In 137, to find the y-intercept, we're going to let x equal 0. So h of 0 is 2 to the 0 plus 5 divided by 2 to the 0 plus 1, which is equal to 1 plus 5 over 1 plus 1, which is 6 over 2, which is 3. So 0, 3 is the y-intercept for this graph. In 138 through 141, we're asked to find the x-intercepts. So in this case, we're going to let y equal 0 and solve for x. So if we let y equal 0, 0 is equal to the absolute value of x minus 4 minus 1. Now we have to undo the operations in reverse order. So if we followed order of operations and replaced x with a value, we would subtract 4, take the absolute value, and then subtract 1. So that means that subtract 1 needs to be the first to go away. That's going to be accomplished by adding 1 to both sides. Now we have to undo the absolute value. So x minus 4, if its absolute value is equal to 1, could be 1, or x minus 4 could be negative 1. Adding 4 to both sides, x is equal to 5, or x is equal to 3, so we have two x-intercepts, 3, 0, and 5, 0. In 139, to find the x-intercepts, we'll let y equal 0, and solve for x. Again, we have to undo the operations in reverse order. So subtract 4 from both sides. And what we need to be aware of here is that a square root may only output values that are either 0 or positive. So a square root can never be negatives. Therefore, this has no solution. We should point out here that you can square both sides, and if you do that, you'll find out that x is 15, but x equals 15 doesn't satisfy this equation because negative 4 is not equal to the square root of 15 plus 1. The square root of 15 plus 1 is equal to positive 4. So that means that there are no x-intercepts. In 140, we can find x-intercepts by letting y equal 0 and undo the operations in reverse order. So we're going to add 3 to both sides. And now in order to undo a logarithm, what we need to do is rewrite this in exponential form. So in exponential form, base 2 raised to the third power is equal to the argument of the logarithm. And since 2 cubed is 8, subtracting 7 from both sides, we get x equals 1, which means that our x-intercept for this graph is the point 1, 0. In 141, we're going to solve for x-intercept by letting y equal 0, and now we have a quadratic equation which we can solve by factoring. I'm going to factor in a box. 3x squared and negative 4 are the first and last terms. 3 times negative 4 is negative 12. The product numbers that are factors of negative 12 that add up to negative 1 are negative 4 and positive 3. So we'll use those for coefficients of the middle term because 3x plus negative 4x is negative x. Now factoring the top column or the left column, the greatest common factor is 3x. The right column, greatest common factor is negative 4, and the top row common factor is x, and bottom row common factor is 1. So 0 is equal to 3x minus 4 times x plus 1. And so either 3x minus 4 is equal to 0 or x plus 1 is equal to 0. And that's going to give us x values of 4/3 or negative 1. So that means our two x-intercepts are the point 4/3, 0 and negative 1, 0. In 142 and 143, we're asked to find the intersection points of the two graphs. So in order to solve this, we treat it like a system. So we're going to set f of x equal to g of x. So x squared minus 3x plus 1 is equal to x minus 2. And subtracting x and subtracting, or rather adding 2, we're going to get plus 3. And that gives us a 0 on one side, which makes it fairly easy to factor. X minus 1 times x minus 3 is equal to 0. So either x equals 1 or x equals 3. And if we check, f of 1 is 1 squared minus 3 times 1 plus 1, which is negative 1. And g of 1 is 1 minus 2, which is also negative 1. That gives us one intersection point 1 comma negative 1. Now let's check f of 3. F of 3 is 3 squared minus 3 times 3 plus 1, which is 1. And g of 3 is 3 minus 2, which is also 1. So we have the point 3 comma 1 as a second intersection point. In 143, we can find the intersection point by setting the two functions equal to one another and then subtracting 2 from both sides and rewriting in exponential form. So if we rewrite it in exponential form, 1 minus x is equal to base 2 raised to the exponent 3. And so 1 minus x is equal to 8. And that gives us an x value of negative 7. And f of negative 7 is the log base 2 of 1 minus negative 7 plus 2, which is log base 2 of 8 plus 2. Log base 2 of 8 is 3 because that's the exponent that I would need to place on a 2 in order to get 8. And then plus 2 gives us 5. Q of negative 7 is 5 because Q is a constant function. The y value is always 5. So that means the intersection point is the point negative 7 comma positive 5. For 144 through 147, given the equations, we're going to identify the parent function and the transformations that will produce the graph. So we see an exponential function here. Its parent is y equals 2 raised to the x power. I see that x has been replaced with x minus 1, which means we have a shift or a translation right 1. And I see that 5 has been added to the outside of the function, which means that we have a translation up 5. In 145, we have a logarithmic function, so its parent is y equals log base 2 of x. And horizontally, I notice that x hasn't been replaced with anything in the transformed function, so that means that there are no horizontal transformations. Outside of the function log base 2 of x has been multiplied by negative 1. That's going to be a vertical reflection, or a reflection in the x-axis. And then 2 has been added, so that's going to translate the graph up 2. In 146, we have an absolute value function, so its parent is y equals absolute value of x. Inside the absolute value, we see that x has been replaced with x minus 3, which means we have a translation right 3. And outside the function, I see that the absolute value has been multiplied by 1/2. So that's a vertical compression of factor 1/2. In 147, we have a quadratic function. So its parent is y equals x squared. And we can see that in the transformed function, x has not been replaced with anything. So that means that there are no horizontal transformations. On the outside, the function has been multiplied by negative 1, which is a vertical reflection, or a reflection in the x-axis. And the outside of the function has also been multiplied by 2. So that means that we have a vertical stretch of factor 2.